So I'm John Spencer. I'm a member of the science team on the New Horizons Pluto mission, and I'll tell you a little bit about the mission and about the spacecraft and how it works and how we designed it to do its job. So Pluto is a place we knew very little about before we went there with the New Horizons spacecraft. This is the best picture that we had until about a year ago. It's pretty hard to imagine at this point, given all the gorgeous images we've now got from New Horizons. This was from the Hubble Space Telescope, the best facility we have for taking sharp images from the Earth, but it's so far away and so small that all you can tell is there's some bright areas and some dark areas. And clearly there was a lot more we had to learn about Pluto to really know what it was like. We did know quite a bit about the atmosphere from watching the Pluto pass in front of stars, and you can see the light of the star dimming as it goes behind Pluto, and that tells you about the atmosphere. So we could kind of imagine a Pluto weather forecast here where it's kind of cold that far from the sun, about minus 380 degrees Fahrenheit, a little bit colder at night, lots of methane in the atmosphere. The atmosphere is mostly nitrogen, like our atmosphere, but the methane is there as well, kind of like water in our atmosphere. So you might have 100% methane humidity on Pluto. Winds pretty similar to wind speeds on the Earth, but the barometer would read about 0.0003 inches, 100,000 times less atmosphere than there is here on the Earth. The atmosphere is very thin, but it's still enough to have winds and clouds and for lots of interesting things to happen. And you'll notice that the day is 3 days long. It's sunny for three days and nights in a row, and then dark for 3 days and nights in a row, because Pluto has a 6-day rotation period. We've known that for a long time. So very different place from the Earth, and a place we really wanted to learn more about. So here's a picture of our spacecraft, and with one of the technicians who's doing the final touches to the spacecraft before it was launched for scale. So you can see it's kind of small. It's about the size of a grand piano. We have a model of it here, and I can show you a little bit about how it works and what the different features are. The thing you notice most is this great big main antenna. We have this very large antenna because it's a long way to Pluto. We need to focus that beam really tightly back at the Earth so that we can communicate back to Earth and hear the very faint signals coming from Earth. The antenna runs on about 60 watts, like the power of an old-fashioned light bulb, and yet we can communicate with it over billions of miles thanks to this great big antenna. This funny spiky thing back here is the power supply for the electrical power that runs the spacecraft. It has plutonium in it, which is very hot, very radioactive, and it's the heat from that decay that generates the electricity that we need. We have cameras on the side here that take color pictures and black and white pictures, and not just pictures, but we take spectral where we can learn about the atmosphere. This is an ultraviolet instrument to look at the atmosphere of Pluto. We can take infrared spectra that tell us about the surface composition, and we can learn all kinds of wonderful things about that using this instrument here. And we have plasma instruments that measure the solar wind there on this side here. So it's a small spacecraft, but it's got a very powerful instrumentation package, so there's a great deal that we can do with this, and a lot that we were able to learn about Pluto with it. This picture here gives you some feel for what the different instruments are capable of. On our way to Pluto, we flew past Jupiter and took pictures of Jupiter's moons. This is Jupiter's moon Io, which is very volcanically active. And the picture on the left is one of the sharpest pictures we can get. That's with our long-range telephoto camera, the LORRI camera, and you can see the crescent and mountains on the rising up into sunlight over on the night side. And then up on the top, you see this bright spot, which is incandescent lava, incredibly hot material from one of these enormous volcanic eruptions. And above that, you see this big umbrella shape of debris that's blasted up from that volcano, and it's rising into sunlight. You can see the shadow of Io cutting across it. In the upper right is an image from the MVIC camera, which is in color, not quite as detailed, but now you can see that volcano is glowing red, as volcanoes should, and that plume is a blue color from the very fine smoke-like particles in it. And then our infrared instrument, LISA, is picking up the heat radiation from the volcano, and it's an enormous amount of radiation. It's that very bright spot, but you can see many other volcanoes simultaneously erupting on the night side of Io. So we weren't going to see active volcanoes on Pluto, but the infrared instrument also tells us a lot about the composition of the surface. So we flew past Jupiter in 2007 after launching in 2006. It only took a year to get to Jupiter, but then it took another 8.5 years to get to Pluto. That's how far away Pluto is, and it's pretty much a straight shot. We did not pass anywhere else on the way. We were pretty busy during that period because we had to plan all the observations we were going to do when we got there. We only had a few hours of time when we were close to Pluto, and we could get all the data that we'd spent 9.5 years traveling through space to get. And so we couldn't afford for anything to go wrong. It takes 9 hours at the speed of light to get a signal to the spacecraft and get a response. And if there was a problem and it had to get help from Earth, the encounter would be over and Pluto would be way behind us by the time you were able to do anything about it. So everything had to be work perfectly on the spacecraft automatically. It had the ability, if something went wrong, to recover itself, to reboot the computers, to get back on the timeline, keep taking data. And so this took years to plan all this, and we rehearsed it on the spacecraft. This diagram here shows Pluto and Charon, which are the brown dots near the bottom, and then their shadows streaming out behind them. The sun is over on the left-hand side. And here's the spacecraft screaming by 14 kilometers per second, pretty much in a straight line coming in from the left. And each those colored bars on this diagram is one observation that it's taking in the colors of the different instruments. So we have red for infrared, blue for ultraviolet, and so on. And so we have this very choreographed sequence of observations as we go past, taking as many images as we can in that very short, very precious amount of time. And then we flew through the shadows of Pluto and Charon and watched the sun setting behind Pluto as seen from the spacecraft. And from that, with the sunlight passing through Pluto's atmosphere with our ultraviolet instrument, we could learn a huge amount about what the atmosphere was like. So that's how we explored Pluto. Here is a picture of us seeing the first images coming in. On the day of encounter, we did not get images down from the spacecraft because the spacecraft was just too busy taking data. So it wasn't until the next morning after we'd all caught up on our sleep, we came in and we got the first pictures back. And here we are gathered around looking at those first pictures. This image here shows the best picture we had before we got to Pluto, and it's already very interesting, shows this beautiful heart-shaped pattern, but the red square at the bottom shows what this first close-up view looked like. And here it is, a very exotic landscape of huge mountains, smooth plains, really weird stuff happening down towards the bottom of the image, weird rolling hills. And no craters, which tells us that the surface is pretty young geologically. It hasn't been, well, it has been bombarded with cosmic debris through the history of the solar system, but geological activity on Pluto has wiped out those craters in these regions and leaves us with this very exotic landscape without craters. So it was very exciting just to see this first image. We could tell that Pluto was geologically alive. The next image I'm going to show you, this is one of our best color images. And this screen doesn't really do it justice. It's huge. It's 3,000 pixels across, incredible detail in it. But we have black and white images with even more detail, and I'm going to show you a scan across along that red rectangle, starting up near the horizon and heading down towards the shadowed regions at the bottom. So here's that scan, and here, this is the northern part of Pluto. It's a smooth plain, but with lots of craters. So this part of Pluto is quite old, probably billions of years old, but there's been fracturing that's happened since then, some interesting kinds of erosion. And as we go south, things get stranger and stranger. We see more of these fractures. Some of them are several miles deep. We can see layering exposed in the walls of those fractures. And we see more smooth terrain. We see more eroded regions as we head south. And then we see these very smooth, bright regions. We think those are lakes of frozen nitrogen that is flowing like a glacier, but it's not water ice like glaciers on Earth, it's nitrogen. And then down here towards the southern hemisphere in the shadowed region, we see, again, these rugged mountains and this feature that looks like some kind of weird ice volcano down in the lower left, and we're still scratching our heads over what that is. So, an amazingly exotic place, and we were very excited to get such wonderful information from the spacecraft. The next picture just shows an example of how we map the composition with our infrared instrument. We can map where the methane is on the left, the nitrogen in the center, carbon monoxide on the right. Each of these frozen ices, which are really frozen gases, they'd be gases on the Earth, but it's so cold on Pluto, they're mostly frozen out on the surface, is distributed differently across the surface, and is telling us about how the ice moves in response to the seasons or to geological activity. And we're having a lot of fun trying to figure out how all those things are connected. And of course, Pluto is not alone in out there. It has a big moon, Charon, which is about half the size of Pluto. Here's a picture of Pluto and Charon that are the correct relative positions and sizes. It's not a pasted up image. This is the actual image we took directly from the spacecraft. And if we zoom in on Charon, this is our best color picture of Charon. It's another pretty exotic looking world. It's got this very dark North Polar region that we think is maybe something to do with Pluto's atmosphere escaping and freezing out on the poles of Charon. At least that's our best idea right now. We have a very rugged region in the north, and then down towards the south we have smooth plains with flow lines. It's like some kind of pasty lava, but it can't be rock lava. It would have to be ice lava, so cryovolcanism we call it, has covered up a lot of the terrain in the south. But there's lots of craters here, so we know this all happened a long time ago. One of the things we've had fun with in the system is we have to have names for things, and so we have names which are still informal, but which we're using to refer to the different features. And on Pluto, we've used various themes for the names. On Charon, we've gone with science fiction and fantasy themes. So here is some of the names on Charon. Some of these are probably be quite familiar to you from your favorite science fiction stories or fantasies. So but it's a lot easier to have names to refer to things than just say, oh, that crater over there. And this is a very good way for us to keep track of where things are on Pluto and Charon. Charon is not Pluto's only moon. There are 4 small moons we didn't even know about when the mission was designed. Here's a montage of them. You can see the edge of Charon down here to see how small these moons are. They're only a few miles across. And they're rugged and cratered and irregular shaped. But what's been most interesting about them is their rotations, which we did not know till we got there with New Horizons. Here's a movie that shows Pluto and Charon rotating around each other, and because of the tides between them, they're locked, always have the same face facing to each other, just as our moon always keeps the same face to the Earth. So this is kind of how we expect moons to behave. This is how well-behaved moons behave anyway. When we look at the rotations of the small moons, you can see they're not behaving in this way at all. One of them is spinning very fast. They're all spinning faster than they're rotating around. One of them is going backwards. Mostly they're actually lying on their sides and spinning end over end as they orbit around Pluto. So we don't really understand this yet. We think it's something to do with the fact they're not orbiting a single world. They're orbiting 2 worlds that are themselves orbiting each other, and that prevents them from settling down into the kind of configuration you would normally expect. So another fun discovery from New Horizons. We're not done now. We're heading out beyond Pluto, out into the rest of the Kuiper Belt. Pluto is the brightest object and the largest object in the Kuiper Belt, which is this vast realm of hundreds of thousands of small objects. And we want to know about those objects as well, beyond Pluto. So we'd always planned the mission, after we flew by Pluto, to visit another world beyond Pluto. But at the time of launch, we didn't actually know of a world we could reach. We only have a small amount of fuel, so we're pretty much heading in a straight line. We can tweak a little bit to the left of right by using our fuel to get there, but we can't make a right-hand turn, a 90-degree turn, and head off in that direction. So we had to find an object that was going to be right there. And it took us a long time to find one. We eventually used the Hubble Space Telescope and used a lot of time on the Hubble telescope. Each of these squares is a patch of the sky that we covered painstakingly with Hubble, covering an area about the size of the full moon in the sky where we expected any object we could reach to be. And we got these data in 2014. We looked through them very painstakingly. We eventually, in the frame that's outlined in red there, blown up here, and blown up again, we found a little tiny moving dot among all those millions of stars. And there you see it. This is a composite of 5 images. You can see the 5 objects circled moving across the sky. And when we plotted the orbit of this object, we found this was an object we could actually reach with the spacecraft. And so after we flew past Pluto, we've fired our engines to set a course to this object, and we're planning to get there in 2019. We're now applying for money to NASA to fund that extended mission, and we won't hear if we have an official mission for a few months yet, but we're hopeful that we will get the money to continue our journey out into the furthest reaches of the solar system. So here's an impression of what this small world might look like. We think it's a irregular reddish world. It's about, we think, maybe 20 miles across, something like that. And we'll fly past this. We'll get our first view of one of these hundreds of thousands of worlds on the edge of the solar system. And then we just continue out into interstellar space, and we'll be able to keep in contact with the spacecraft through about sometime in the 2030s before we finally lose contact, but the spacecraft will keep going on forever, which is pretty mind-boggling. So that's the story of New Horizons, and it's been a pretty exciting mission to be part of, and thank you. Part of, and thank you. Part of, and thank you.